Out, and we are now live. Okay. So my question to all of you is, what is happening next week? And remember, everything we do is on the website. So next week, if we go to our quiz and review date sheet page, next Thursday is exam one. It'll be delivered on eCampus virtually. You have to have a computer that has good Wi-Fi or direct internet hookup. And I and my proctors will be in this room, so you're welcome to come here and take your exam here. I think, have you been getting good Wi-Fi here during lecture? Yeah, so you probably, if you need reliable Wi-Fi, come here. Or if you think you might have a question for me, come here, and that way you can access me directly. Your call. Wednesday night at 6, I will set up a Zoom meeting. Same link is coming to lecture. Okay. And then after exam one, I'm going to set up a weekly Zoom session, probably like Tuesday afternoon at 5 or 6 for you just to log on if you have any question for me. Kind of like a Zoom office meeting standing. I usually log in whenever it starts and wait about 15 minutes. If nobody else logs in, I just log off. Somebody logs in, we stay there as long as we need. Cool? So be ready for your exam next Thursday. Please look at some old exams on the quiz file to see what kind of exam I get. The depth of my question, which I think is pretty deep. So let's go to our lecture supplement, and let's go to the end of anatomy. We need to call up the fruit. We're through with the flower. So the last thing we need to cover in anatomy is the fruit. So go to page 19. Page 19, let me make this small. Okay. Page 19. Excuse me, page 20. You might want to keep your notes on page 19, but I'm going to keep my picture on page 20. So the ovary of the flower develops into the fruit. The wall of the ovary develops into the fruit wall. The wall of the ovary doesn't have a unique name. It's just called the wall of the ovary. They missed their chance to create a whole new name. An orange is made up of sections, right? Peel of orange is made up of sections. Technically, we call those sections carpels. So a fruit is actually a carpel. Orange has many carpels. Some fruit don't have sections, so they just have one big carpel. If you cut a tomato, you'll see, you don't see sections, but you see like what we call locules, little gaps, and then meat between them. Well, each one of those sections is like the section of an orange. So the fruit is really a carpel. So the fruit wall is called the pericarp. Para means outer, perimeter, outside. Pericarp, the wall surrounding the fruit. On some fruit, you can see up to 3 layers. If you look at a peach fruit, you can see up to 3 different layers. And they all end in carp, for carpal. What does exo mean? Outer, meso, endo. Okay, so the exocarp is the outer fruit wall, the mesocarp is the middle fruit wall, and the endo is the inner fruit wall. And on a peach, you can see all 3 layers. The fuzzy skin is the exocarp. The pit is the endocarp, and it's hard and bony. Okay, and then the part you eat, the fleshy part, that is the mesocarp. Okay, have you ever broken a peach pit? Oh, huh? Off campus, you can't see what I'm sharing?
No, we could see it.
You can't see it. Why not?
We can see it.
No, but on
He's
campus,
talking about people there,
you
yeah.
can't see it. Why? Huh? Why does something screw up what did I do? No, there's a setting where you set duplicate display, which tells my computer to send it here and there, but I didn't change anything. But when we started, you could see it, right? You never could see it? Well, it took y'all a while to tell me you couldn't see it. Okay, he showed me how to do that one time. It's in, I'm gonna have to stop sharing. It's in settings.
It's in your system and then display.
In my computer's system. How
Yeah,
do I?
settings, and then press system after, and then display. And then it'll give you a drop down of the different display modes. And what you actually want is you want, I mean, you could do duplicate and that'll show what's on your screen on the big screen, or
Okay,
you can do continuous, which is 2 different screens that you can scroll between.
okay. Step one. Where is?
Settings, and then system.
I know that little gear is settings, and then system,
Mm-hmm.
and then
Display.
display. That was not where he went.
Mm.
Maybe duplicate. Yes, yes. That I took a picture of that, but then I'm looking at my picture and I'm going, I've never seen that screen on Zoom before. It ain't in Zoom, it's in your computer. Oh, now you see why people like me have no business even attempting new learning curves. Lord have mercy. Thank you, thank you, thank you. Okay, I got it. Okay, I did it. I just have to do click keep changes. I'm gonna make it little instead of closing it. You guys are funny. Oh, there we go. Hallelujah. Hallelujah. Okay, I need to, I won't get that back. No, I'm not sharing. I should see my camera, right? How come we in here don't see me full screen? I'm not sharing. Okay, I'm going to share now. My goal this semester is to have one entire lecture without something messing up. Okay. Not every fruit is fleshy. Okay. For example, a corn fruit, a kernel of corn, what you probably call a seed. Okay, you go buy a bag of corn seeds. Come on, pop down menu. Let's go there. Let's go there. You go buy a bag of corn seeds, and you think that's a seed. That's not a seed, it's a fruit. Okay? The seed is inside a fruit. The fruit is attached to the tree. If you pull something off of a tree, what you have in your hand is the fruit. You peel the paracord back, what you have in your hand is a seed. So I take a peach, I cut it open, I get the pit out, I hit it with a hammer. I look inside, I will see a seed that looks exactly like an almond, because almonds are in the peach family. That's the seed. Corn, where do you get it from? You take it off the ear. So what you have in the hand is the fruit. But the fruit wall is dry. It's just another dry layer outside the wall of the seed. So actually, corn seeds are fruit. How many of you eat corn, you get stuff stuck between your teeth? That's the fruit wall. It's a little bit harder, okay? Name me another fruit that you pick off of a tree and you've always called a seed. Sunflower fruit. Sunflower fruit, you pluck them out of the flower head. So those are fruits. Almost all of our nuts that have a husk are fruits. So anything that you have to peel to get to the seed, that's the fruit. Is a peanut, is a shelled peanut, is that a fruit or a seed? It's a fruit. It's a dry fruit. You peel it, and inside is the seed, the actual peanut that you eat. If you take that seed inside the peanut and break it open, it'll be in two halves. Okay? And if you look closely inside those two halves, one of the halves will look exactly like this bottom diagram. One half will have a little bitty torpedo-shaped rod with little bitty, it looks like a fan or fingers of feathers. That's the baby plant. That's the embryo. And the embryo is a long shank, which is the stem of the baby plant, of the embryo. We don't call it stem, we call it epicotyl and hypocotyl. And at the tip, you have some little bitty baby leaves we call the plumule. And we have a little bitty root tip that we call the radicle. And all of this together is called the embryo. It's a young plant. Seeds have a navel. That scar on a black-eyed pea, that's where the seed was attached inside the fruit for nourishment. And when it breaks off the navel, they call the hilum. Just below it, you see a little pinhole. That was a pinhole for fertilization, where the pollen tube grew. Okay? So that's the reproductive part. We have the fruit with up to 3 walls. If we see the walls, we give them the name, endo, exo, mesocarp. If we don't see it, we just call it pericarp. Inside, we'll find the seed. Seed is going to have an embryo. Plumule, epicotyl, hypocotyl, radicle. And those two halves on a peanut are called cotyledons. They're the first leaves. Sometimes we call them seed leaves because they're leaves inside the seed. And they're full of stored food. Like an egg stores food in the albumin, chicken egg. Fruit stores food in the first leaves, big fat cotyledons. How many cotyledons in a peanut? How many cotyledons? How many halves? It's not a trick question. 2. There are 2 cotyledons in a peanut. Oh my goodness, it's a dicotyledon? That's where the word dicot comes from. A dicot is a plant that makes fruit and seeds where there are 2 cotyledons. It is a dicot. That corn fruit, there's an embryo in there too, and it has only 1 cotyledon. And that's where it gets the name monocot. Okay? So we get the name from going all the way back to their seeds. The wall of the seed is called the testa, or the seed coat. Sometimes it's soft, like beans, you cook them and eat them. Sometimes it's hard, like a pecan. You have to crack them to get at the cotyledons inside. Hey, how many halves in a pecan? 2. I wonder if it's a monocot or a dicot. Dicot. So next time you eat a seed where you crack it open, you get 2 halves. Say, hey, look, it's dicot here. Yeah. That's where we get the name. Okay, so know the layers and parts of a fruit and of a seed. They are defined for you on the previous page if you are a read-write learner. Cool? Any questions about fruit, seed, or anything about anatomy? No? Okay. I'm going to stop sharing. And I'm going to come back to, oh, that's a good view right there, isn't it? So now what we're going to do is do chemistry. Only 2 chemical reactions in plants that we'll study: photosynthesis and respiration. Let me share. I want you to help me. So I want to share. Let me create a whiteboard. There we go. How many of you told me you liked chemistry? How many of you like chemistry? Okay, you can't answer any questions in this first part. How many of you don't like chemistry? Okay, you will answer every question in this first part. Okay? I want to write on this whiteboard the chemical reaction for photosynthesis. Somebody who doesn't like chemistry is going to give me the answer. Somebody start and tell me how to write the chemical reaction for photosynthesis. CO2, C, O2. Huh? Is that how we write it? Huh? CO2. Is that how we write it? How do we write it? The 2 is subscripted. What's the C? Small or capital? Okay, so y'all told me wrong. Let's start over again and tell me how to write the equation for photosynthesis, but be more explicit in your instructions. What? No, what am I writing? Big C. Could we call that a capital C? Okay. Capital C, capital O, subscript 2. Is that right? Okay. Plus sign. Capital H, subscript 2, capital O. Arrow pointing right. Okay? Capital C, subscript 6, capital H, subscript 12, subscript 6. Okay, somebody who hadn't talked yet, that doesn't like chemistry. Plus sign? Like that? Oh no, I just want the equation. Is the plus sign right? Capital O? Okay. That is the chemical equation for photosynthesis. Does it have numbers? Huh? I just want the equation. Just the chemical equation. Is that the chemical equation? Yeah, it's a chemical equation. That's every chemical equation in the world. Some chemical symbols on the left side representing elements and compounds. An arrow, which means, hey, it's going from here to there. And then the chemicals that are produced on the right. It's a manufacturing process. It's a shorthand. If it was a bicycle manufacturing plant that I wanted to describe to you on your first tour, I would have on the left side wheels, handlebars, seats, spokes, pedals, plus, an arrow to the right, and I draw a picture of a bicycle assembled. And then in the process of assembling it, we always had extra parts left over. Boxes and things that was holding it together, a bunch of scrap. And I'd have a little pile of scrappy things that we're going to throw away. Okay? And that's what photosynthesis is. I will never put the numbers. The numbers is only to confuse you. You know? So I will always only put the raw equation by itself. The next level class can balance that equation with numbers. Is there a name for CO2? Carbon dioxide. Is there a name for H2O? That's that old buddy water. Is there a name for this thing right there? Somebody say sugar? Is there another name? Glucose. Somebody say glucose. Is there another name? Carbohydrates. We can call a lot of different things. The specific sugar it is glucose. Okay, and what's this fellow right here? Oh, buddy, oxygen. So if I wanted to say photosynthesis in the form of a narrative, I'd say we take CO2 in the presence of water. We produce a sugar called glucose and a byproduct called oxygen. Okay? So I thought you told me you didn't know and didn't like chemistry. You know that. You know why you know that? Because they had the formula for chemistry for photosynthesis, I think, starting in the 2nd grade. I didn't see it until junior high. and when I went to school. But I noticed in my grandkids, man, they started to slap them with that kind of stuff way back to the 3rd grade, kind of brainwashing towards that. This is just how chemists write their reactions. It's a flow chart. It's hieroglyphics to you, though. Now, what makes it really confusing is sometimes they won't even put the chemical symbols. They draw the picture of the molecules, you know? And that's another order of complexity. You have to recognize the stick diagram of how they draw molecules, and then the equation diagram for how they use from the periodic table those symbols for each element, okay? So, but keep in mind, and nothing more than how chemists talk. Everything goes from left to right. Every equation I give you, photosynthesis and respiration, goes from left to right. And keep in mind, it's a manufacturing process. Something will take a CO2 molecule and take a water molecule and figure out a way to break it apart and reassemble it in the form of a glucose. Every carbon that is in the CO2 will end up in the sugar. Okay? So if I'm building my house, the truck from Lowe's drives up and dumps all kind of parts on the ground. 2x4s and 2x6s and sheetrock and sacks of concrete and nails and screws and all kinds of stuff. Okay? Something takes all of those parts, uses them to reassemble the final product, glucose. If I'm assembling a bicycle, what goes out the door is the bicycle. That's the final product we're trying to do. I'm going to tell you, if you could see photosynthesis happening, if you could watch the glucose literally being built, it would be as simple as watching a manufacturing bicycle plant build a bicycle. How many of you are already dads or mothers and are aunts or uncles or have younger siblings where on Sunday morning you spent your time assembling toys for them? Pretty dang complicated. But if you take it step by step and don't skip steps like people like me do, you can put together a pretty complex toy with the right instructions. Okay? But if you do it with a bicycle, you're going to recognize the parts. So it makes it simple. The reason why you don't like chemistry is you can't see, touch, or feel, and you've never seen a CO2 molecule or a water molecule, so you can't identify with it. So if you don't like chemistry, or if you don't think in the form of chemical equations, all of this is abstract to you. How many of you is chemistry abstract to you? Like Egyptian hieroglyphics. I can't flip and read it. Yes, you can. You read that message quite well, okay? So what I'm going to do today is I want to go through the steps of photosynthesis of how the manufacturing process occurs, and I'm going to want you to do more listening than actually writing. But let's set the stage. Let's unshare, and then let's reshare, and let's come here, reshare, and let's go backwards. And turn to, if you're following your notebook, the physiology of plants. And the first step in the process is photosynthesis. So here you guys are seeing photosynthesis, and off campus, are you seeing the shared screen from page 21?
Yes.
Good. Hey, have I frozen up yet? Have I frozen yet?
Not at all.
Okay, so where does photosynthesis occur? It occurs inside the chloroplast, and they are green. What is the name of the pigment, the green pigment that makes them green? Chlorophyll. I bet you all of you know that, okay? The definition of photosynthesis, we write it out in the narrative, is what we just went over. It's a process where a plant takes carbon dioxide, water, uses it to produce carbohydrates and oxygen. Oxygen is a byproduct, okay? So if I give you the definition of photosynthesis and you miss it, if I give you that definition, say what reaction it is, and you don't pick photosynthesis, I'm gonna fail you. Sorry, you failed. Okay? And it happens inside of the chloroplasts, which are a green plastid. What's our name for colored plastids? The generic name for any colored plastid? That'll be about question 4 on the exam. Plastid, colored plastid. Mama, don't take my Kodachrome. Chromoplast. And if it's a green chromoplast, since it's so special, we call it a chloroplast because it contains chlorophyll. Chlorophyll is the green pigment that is central to photosynthesis in the plastids. Now, inside the chloroplast, it has 2 parts. It has a bunch of membranes, okay? Each individual membrane is like a flat sac, and we call that the thylakoid, and they're stacked together. And when they're stacked together, the stack is called a grana. And the stacks of grana are connected by tubes to communicate, and they're called grana lamella. The first time I saw this picture, what popped in my mind? Pancakes. Pancakes. My goodness, they looked like a stack of pancakes. Project 1 is you may take some diagram and make a 3-dimensional model. One year, somebody made a model of a chloroplast, and they went and cooked some green pancakes. And that was their thylakoid, stacked them together to make the grana. Pretty good. And then what would the grana lamella look like connecting to pancakes? Maybe a long, thin pancake with a hole in the middle? Yeah? Or maybe a straw? Or a bamboo stick with a hole in the middle or something like that. Some of the reactions occur inside the grana. And I'll tell you right now, the reactions that occur inside the grana is the one that we call the light reaction. The light reaction is the reaction we're going to see in a minute that is the reaction that uses light. So we call it light reaction. The grana are floating around in a fluid matrix called the stroma. So what popped in my mind then? The pancakes are floating around in syrup. Yeah, syrup. Yeah. And it's clear because there's no pigments in it. And then it's surrounded by 2 membranes, the membrane. They didn't give the membrane name of the chloroplast a special name, but it just has 2 membranes. So when I saw this, I said, yeah. The way I remembered it was stacks of pancakes connected with straws inside an M&M, not loaded with chocolate, but loaded with syrup. And I never, ever forgot the structure of a chloroplast again. Okay? So know all these parts of the chloroplast that are used in photosynthesis. And there's our equation at the bottom. One thing we didn't put in our equation was, in some equation, in some books, they will write things on the arrow. And the things written on the arrow are usually things that are really part of the reaction or drive the reaction or have to be there for the reaction to occur. And I think you all know that photosynthesis must have light. So we write light right there. Chlorophyll is so doggone central to the process, they very often write the name chloroplast on the arrow because it's going to only happen in a green plant. And that's your classical definition. And it's balanced in chemical equations. So I balanced it in my notebook, just so people would know I knew how to write a balanced equation. But I will never ask you on the exam any of the numbers type of deal, okay? I also on the exam have a lot of trouble writing the superscript and subscript in eCampus. So I will usually write out the whole word, carbon dioxide, oxygen, water, yada, 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 okay? And like I said, there's 2 reactions. Most people think it's 1 reaction, but there's really 2. The light reaction is a reaction that uses light, and sometimes it's called the Hill reaction, but I will always only call it the light reaction. And then there's another reaction in photosynthesis that doesn't need light, and we call it the dark reaction. Oddly enough, we're going to see that it doesn't happen in the dark, okay? The light reaction does happen in the light, but the dark reaction doesn't happen in the dark. but we still call it the dark reaction. So there's two reactions. I'll tell you right now, the light reaction occurs in the grana. The light reaction occurs inside the pancakes. The dark reaction occurs inside the fluid stroma. So you might want to write there. Light reaction occurs inside the grana. Inside the grana. Inside the grana. Annotate, buddy. Let's draw it. Doot, doot, doot. Light reaction occurs inside the grana, and the dark reaction occurs inside the stroma. And the light reaction occurs first. Light reaction occurs first, then the dark reaction occurs. All of them occur inside the chloroplast. You want me to show you why you don't like chemistry? Or maybe don't understand chemistry? That's it right there. If you look in plant physiology or plant biochemistry or even plant botany text, all these chemists write the reactions in the form of equations. Okay, how come I can't get annotation to pop up? Is that because I'm already annotating? Go to the green. Oh, there it is. I wasn't going high enough. Okay. So what I tried to do is generate one diagram where I put a reduced version of the actual biochemical cycle where it is occurring. Okay. So I just told you that the light reaction occurs inside the grana, and that's my cutaway view of a grana. Okay? And then the dark reaction occurs in the fluid stroma. Okay? In the light reaction, water is split and oxygen is made. That is a separate chemical equation. Okay? It's in the stroma, in the dark reaction, where the carbohydrate or glucose is assembled and oxygen is produced as a byproduct. So the light reaction and the dark reaction, two separate reactions, occur in two separate places at two separate times. But the light reaction occurs first. What chemists will do is they'll sometimes take a reaction that has a bunch of steps and they'll write them out, and then they'll draw a line, and then they'll give you one overall net equation of things you started out with and things that you ended up with. And that's what the reaction of photosynthesis is that we have in all books. I don't think I've ever seen a lower level book that had the light reaction written out as water to oxygen and carbohydrate I said water to oxygen. Carbohydrate to water. I mean, it's CO2 plus water, with the reaction. So we're going to take each one step by step. Now, I want you to close your notebook and not write anything. I want you to just listen to me and watch me. Okay? I'm going to walk you through that reaction the way I learned it, the way I did it, where it made sense to me. Okay? You just listen to me and see how much you pick up. At the end, I will tell you what you need to know for the exam. And I'm telling you right now, more than half of what I'm going to tell you will not be on the exam. I'll distill it down to the basics. Okay? So just sit back and watch the movie. Okay, let me erase. Let me try to erase. Okay, I am going to, you keep this page in front of you. I am going to call up a whiteboard. And I want to, how do I erase the whiteboard? Clear all? Uh-oh. No, I got there. Clear all drawings. Cool, good. So let's go back here. Okay, light reaction occurs first. You will see at the bottom of the page, I have an arrow come up labeling water. The first thing the plant will do is split water. It will take one water molecule and it will split it into hydrogen. And when hydrogen is by itself as an atom, it is always positively charged. And when the oxygen is released, it will always combine with another oxygen immediately and make an oxygen molecule. Okay? So that's where the hydrogen and the oxygen ends up. When water is split, though, something else is produced. Does anybody know what it is? It was something that was helping hold the hydrogen and the oxygen together. An electron. And we always put it as a small e, and it is always negative. Now, notice we have a positive hydrogen and a negative electron. Charge balance has to be maintained. In nature, you can't have separation of charges. The reason why hydrogen has a positive charge is an electron is pulled out. In fact, in the process of pulling out is what makes it split. And then the hydrogen goes positive, the electron goes negative. Okay? Is an electron a form of energy? Yes. I have some right here in this battery, a form of energy. There's electrons in there. Okay? Yep, it got some in there. I just kind of shocked my tongue. How many of you check the power if you have energy in a 12-volt battery by licking the two poles? Yeah, I've done that too. Yep, it got energy there. Okay, so the energy is stored in there. Can those electrons be used for doing work? Yeah, they could drive any kind of electrical motor. And what you don't realize that in the world of chemistry, electrons power many chemical reactions. In the process we're talking about here, water is split and an electron is released. So the energy that was in the water in the form of an electron circling the molecule in some kind of orbital is now kicked out and it's sitting by itself as an independent free electron. Okay? That's what a solar collector does. Flat sheet with a little catalytic surface and sunlight hits it and it kicks off free electrons and we collect those electrons from a solar collector and we use that as electrical energy source. The plant has figured out how to split water and produce electrons. And it doesn't take effort. We don't know how that happens. The brightest people on this planet have tried to figure that out forever. How could I take pure water, split it into hydrogen and oxygen, and harvest those electrons and do it where it takes less energy to drive the reaction than is produced? And we can't figure out how to do that. Plants do it. Plants produce electrons basically effortlessly. Okay? If you can figure out how to do that, you will not only be rich, you will own the world. Because the most abundant resource we have on this planet is water. If you can figure out how to get electrons, electrical energy, out of pure water, with the byproducts being hydrogen and oxygen, which, by the way, are not polluting, they're natural, you will have a pollution-free, limitless source of electrical energy. You will literally own the world. That patent would make you and all of your heirs quadrillionaires. But we don't know how to do it. Okay? Now, when that electron comes out of that water, it has a certain amount of energy. And I envision the energy in an electron from its momentum surrounding the molecule. You know, in a water molecule, we have an electron in one of the orbits, probably a pi orbit, but I don't know for sure, and it's moving up and down, up and down, up and down, up and down. okay? And it's kind of an energy source. I wonder how much energy is in there. That wasn't bad. That was enough energy. Okay. Oh, ow, God dang it. I didn't mean to do that. But it didn't hurt. I felt it, but it didn't hurt. I'm disinfecting it. Okay? Who would be willing to stop it with their hand? Now remember, I disinfected it. Who'd be willing to stop it with their hand? Would you? Okay. Did it hurt? No, but did it feel it? The energy's now in your hand? Yes. Okay? If you go stand in the sun and collect sunlight, radiant energy, and convert it to heat energy, you're converting energy to another form. So that electron in water is pretty wimpy. And when it comes flying out of the water molecule, let's see how high, let's see how much energy it has to see how high it can go. Oh, went about what, 10 feet high and about 10 feet that way? Yeah. That's a pretty wimpy energy source. That one electron is incredibly wimpy, okay? But let me tell you what happens is, inside the plant, this happens inside the grana. Inside the grana is also chlorophyll. Okay? So here comes Mr. Chlorophyll. Okay, here comes Mr. Chlorophyll. Okay, let me do this. Come on, spray. Ethanol. Give me some disinfectant. I have everything disinfected. Would you be willing to swing it around? Okay, like grab it like about right here, and just do like that, okay? And then what I want you to do is, I want you to shoot it right at me. You know, fling it, see if you can shoot it right at me. No, you know, it's not that powerful. It's not that, about like that. That's about how powerful it is. Okay, come on. Oh, you see that? Did you see it? Did you see me grab it? Did you see me grab it? Oh yeah, do I look kind of excited? That's what happens. When water is split and the electrons can fly out, chlorophyll grabs it because it's a pigment. It's a light harvesting pigment. And when it does that, it now has one more electron in its orbital. So chlorophyll is like sitting inside the ground of the chloroplast, just chill. You know, if you could see a molecule, it has its act together. Just chill. You can tell it has some energy. It has it under control. Not schizophrenic like freaky, just, yeah. But as soon as it accepts its electron and absorbs it, which it has to, then it has one more electron in its orbital, and it gets all loppity. Okay? It's a pigment. What else can it do? It's a pigment. What else can it do? It can absorb. A pigment can absorb. Light, freaking light, yeah. So chlorophyll can't help it, but it's going to absorb light. And when it does, the light energy is not going to heat it up. The light energy is going to make it take the electron that's making it kind of loppity to a higher possible orbital. Listen, can you hear it? Can you hear it? But then chlorophyll is going to be like, oh, and it will be so excited. It has two choices: break apart and destroy itself, or spit that sucker out. Okay? When it comes out, all the energy that was in the light chlorophyll absorbed is now in the electron, in that higher orbital. So I'm going to try to shoot it straight up. we can test the amount of energy by how high or how far it goes. So to be safe, everybody, well, you guys were already in danger. The least common place is here. So I'm gonna send it. I want you to cover your face and maybe your book in front of you. In case I don't get it up, I get it going that way, okay? So literally, chlorophyll would absorb the electron, get a little loppity, absorb light, get freaky loppity with the electron right there, okay? Now, it's gonna spit it out. Okay, let's try this. Oh, you ready? You ready? Okay, zoom, 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 zoom. Wow! Holy moly! Yo, did you see that? That looked like a Nolan Ryan fastball, baby. Okay, would you spin it and throw it at me and I'm gonna catch it? Would you? I don't even know where it's at. Wow, wow. Would you spin it and throw it at me full speed like that? You won't have any choice, you're gonna have to hurt me. Would you be willing to do it? If you're willing to do it, I'll try to catch it. If you put my eye out though, it's gonna be on you. Huh? You crack my face shield, it's gonna go through the face shield in my eye out the back of my head. Would you feel guilty? Okay, I don't want you to feel guilty the rest of your life, so I'm not gonna ask you to do it.
Okay, thank you. I don't want to hurt you.
There is a molecule, compound inside the chloroplast that can grab that electron. It's called an electron transport carrier. I envision it as Nolan Ryan and Pudge Rodriguez. I know all of you know who Nolan Ryan is. 101, 102 mile an hour fastball. Pudge Rodriguez is one of the greatest catchers in the history of the world, next to Johnny Bench. He caught Nolan Ryan. He caught Nolan Ryan's fastball like you and I would play pitch and catch with a tennis ball. Come on, no, right here, baby. Hup, come on, baby. Hup, yeah, that was a good one. Come on. Give me all you got, no. Come on, right here, baby. Hup, yeah, that's all it is. These electron transport carriers, when that electron comes flying out of there at 1,000,000 miles an hour, that comes out the speed of light, they grab it, and it makes them equally excited, okay? But in a controlled way. They don't fly apart, okay? Can you imagine me catching Nolan Ryan? Like if we really tried it? Come on, no, right here, baby. I wouldn't even get my glove up. But these guys can catch that electron, and now they have it resident in them. I envision them to be Arnold Schwarzenegger. I'll be back. That's some energy, right? That's some power and energy. So what happens is the electron will come flying out, zoom, 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 zoom. Oh, you guys are perfect. There's about 4 of them, okay? You're gonna be the first one. I'm gonna fling it out like in slow motion, and then you're gonna catch it. But when you catch it, you have to express the total amount of energy that is now in you. What is your excited state? Let me see it. What would be your excited state? Okay, when you catch it, you have to do that.
Okay.
And then you're gonna pass it. You're like chilling. When you absorb it, you're gonna get excited. What's your excited state? Okay, as soon as you get rid of it, you go back to your chill. Then tunna, okay? Then tunna, and then tunna. Okay, now to make sure we don't get each other infected. Hey, look, we taking, uh-oh. Uh-oh. Okay, now, I need to focus the camera on what's gonna happen. Okay, so cameras, camera, I need to stop sharing. I need to come back here. I need to go to east-south camera, I think. I'm on dot cam. I want to be on camera. I want to be on. Oh, I'm on display B. Camera. Off campus, do you see the camera? Okay, I want to be over here. I need that camera east. I think that's south camera. Okay. Hey, wave you. Oh, yeah. So this is going to be our electron transport chain, starting right here, okay, for people off campus. For you, you won't be able to see, you'll have to look at the screen. So I'm going to go chlorophyll in slow motion, act like it's a NOLA run fastball. You're going to catch it. You're going to get excited. You're going to pass it. You're going to cool down. You're going to get excited. You're going to pass it. You're going to cool down. You're going to get excited. And we're going to go all the way. Couple of rules. You can only hold one electron at a time. Okay? Only can hold one. You can only get rid of it by giving it to the next one. That's your only choice. Okay? There's a lot more chlorophyll. As soon as I get rid of the electron, another water's going to split. Another electron's going to be flinged out, and I'm going to absorb another one, and I won't get excited. I'm going to absorb some light. I'm going to get even more excited, and I'm going to give you another electron. So we're going to keep doing that until we threw it all these electrons. Okay, so water splits. I got it. Oh, yeah, I'm good. I'm good. I think I'm going to absorb some light. Okay, baby. Yeah. Here it comes. Yes. Okay. Like that. Boom. Light. Yeah, you better bet. Yeah, okay. Not everything's waving. Give me a different kind of excitement. Yeah, I mean, y'all just so copycat. Electron splits. I got another electron. Supercharged. How many electrons you have? You got 4. You can only do 1. Hold one. Put them other 3 back. You can't have them. Get rid of them. Send them back. Send them back. You can only hold 1. Yeah. No, I dish it out. I don't take it. Okay. No, you can't only hold 1. Where's the one you held? Oh, you each got 1. Okay. Move, do it. Move, come on. Get rid of the electrons. Come on, I got another one. I blow apart. What's our problem? We have electricity flowing. It has to have a place to go, right? A plug, an electrical plug has electrons at the surface. They're not going to come out until you plug it, give it a place to go. We need something to take the electron from the one on the end so more can flow. On the diagram, what's at the end of the electron transport chain? NADP positive. NADP positive. NADP positive. Yeah. NADP positive. Yeah. NADP positive. Yeah. So you're going to choose over. You're going to take the electron, get just a little excited because it's been sapped of most of its energy. Little excited, okay? Then go back and sit down just a little bit in a minute. Then you're going to take one. As NADP takes them off the end of the chain, you guys can start moving it up. Okay? Now, it's an electron. It's negatively charged. I said you can't have a negative charge by itself in nature. It has to be neutralized by a positive charge. What is released that has a positive charge? A proton is called this is clean. That's food. It's clean. It's clean. It's clean. That's a hydrogen. That's a hydrogen released, split into water. It has a positive charge. Where the electron goes, the hydrogen must follow. So each one of you come get next to one of the electrons. You don't need to get close. You're going to be a 6-foot hydrogen. Okay, 6 foot, 6 foot, 6 foot. There's only 3 of you. No, not too close. We got to be socially distant, else I'll get sued. Okay? As your electron moves up the chain, you follow it. Okay? So watch it. That's your electron. That's your electron. That's your electron. Okay. NADPH. NADP. Go get your electron. Go sit down. Just chill out. Okay. NADP. Come on. Come on. No, you got it. It's yours. Go sit down. Be a little energetic. Go get your electron. Hey, wait, what was my hydrogen? No, NADP had a positive. They neutralized it. They neutralized it. You're good. It's neutralized. No, it's the hydrogen is neutralized.
Okay.
You have no positive charge to go to. You just stand here like nothing. Yeah, come on, let's go. Let's go. Move the electron. Stay with your hydrogen. Okay, go get your, go. Yeah, okay, go follow it. Oh no, it's neutral. Go back up there. Go. We need another, albeit. Go. Okay, I'm neutralized. Okay, everything is through. About 6 waters were split. About 6 electrons came through. You guys all got excited. You guys now have the electron. It's kind of wimpy, but it's a power source. You are a metabolic energy source called NADPH, and you guys are hydrogen. Okay, and you're sitting up here naked. Yeah, but they're also concentrated together. How do things diffuse from high to low? You only came up because you followed the electron and pulled you up. As soon as you lose your electron, you have to flood back down. This is the energy gradient. You have to flood back down that energy gradient at breakneck speed. Go, fast. Come on, go. Oh, thank you very much. Just go about your own way. You're through. That's photosynthesis. Where is the energy? Where is the energy that was in the chlorophyll, that was in the water, that was in the electron? Where is it now? Some of it's in our NADPH, okay? And then as the hydrogen floods back down, it dissipates the energy gradient. And that energy gradient and that flow of hydrogen powers the production of ATP. ATP is adenosine triphosphate. It is the most common metabolic energy source for every cell on this planet, plant or animal. What has the plant done? The plant has taken water and split it to produce a weak electron as an energy source. Chlorophyll has taken that electron, brought it into itself, trapped radiant energy to bring that electron to a higher level of energy, spit it out, and powered the electron transport chain to create a massive energy gradient. Okay? If we were going straight up, and if I had used a 5-pound ball for the hydrogen, and if you were 15 feet off the ground, when you lost your electron and they lost their electron, that 5-foot ball dropped straight down to the ground. How much damage would it do down here? A lot. A metabolic energy source, so the hydrogen coming back through does the same thing. It's almost like water flowing down a dam to produce electricity. The movement of things can be used to produce energy. The energy is used to make ATP. The plant has taken an electron from water, supercharged it with radiant energy, and used a metabolic process to produce ATP. What kind of energy is ATP? Is that me? Is that me? It's chemical energy. The plant has produced metabolic chemical energy from light. Only photosynthesis can do that, and only green plants can do that. So what is the input from the net equation of photosynthesis? CO2 plus water equals carbohydrate plus oxygen. What is the net equation for the light reaction? Water, oxygen. That's the process that uses water, gives oxygen as a byproduct. Where's my marshmallow people? I'm sorry. Where's your marshmallow? Oh, I'm sorry. I'm sorry. You can't hang around. You're a byproduct. You're a byproduct. Okay? You're a byproduct. You have to diffuse out the stoma, the portal, the opening that lets you out of the leaf. Get out. Get out. If you were the oxygen molecule, find a stoma and get out of the room. If you want to, you can throw your marshmallow out the door and come on back. Oxygen is the byproduct that's spit out. Now, the marshmallow now is representing oxygen, not the electron. Okay? Yeah, y'all can come back, but not with a marshmallow. Oh, they might be going out the real door. Okay? Every molecule of oxygen you've ever breathed in your life was produced from this reaction. There are other chemical reactions that make oxygen, but the oxygen on this planet comes from photosynthesis. You breathe tell them they can come back. I know they want to come back because yeah, come on. Where y'all been? You went and got some coffee? Yeah, thank you. Y'all actually were oxygen diffusing out, not hydrogen. I just used the marshmallow for oxygen. I should have had somebody with a marshmallow sitting over here, oxygen the whole time. Okay, light reaction. Water to oxygen, ATP is produced. What happens next? Let me share the screen. Let me share the screen. First of all, I'm sharing the screen. Did that come anywhere near making sense? Okay? So now this is happening inside of the grana. What we need to do now is we must make the glucose. Okay? So what happens now is over here in the stroma is a standard biochemical reaction that's used to construct the glucose molecule. Now this is like any biochemistry. And if you look at any biochemistry reaction, you have a couple of substrates and you have an enzyme that puts them together and catalyzes their union or their destruction, and it assembles the molecule. So the dark reaction is going to occur in the stroma, and it's going to be the reaction with just classical biochemistry constructs a glucose molecule from carbon dioxide. So what will happen is carbon dioxide will diffuse into the leaf through the stoma and find itself inside the grana of the chloroplast. Inside the stroma of the chloroplast. Inside the chloroplast, there is a 5-carbon sugar. Do you need to know numbers? Never. There's a 5-carbon sugar called ribulose bisphosphate. Do you need to know that word? No, but it's made out of 5 carbons. Okay? It's made out of 5 fingers, so to speak.
Go to bed.
What?
Go to bed, King.
Did y'all understand that?
I think she didn't know that I think she meant she muted.
Can you hear me?
Yes, we can hear you.
Oh, okay, cool. So we have a 5-carbon sugar, ribulose bisphosphate. There's a carbon dioxide molecule diffusing through the stoma. It can be represented by one more finger. An enzyme will grab those 2 molecules, position them close together where a 6th carbon is connected to the 5-carbon ribulose bisphosphate to make a 6-carbon sugar. As soon as that happens, as soon as it's made, it splits in 2 to make 2 3-carbon sugars, phosphoglyceric acid. So now I have 6 fingers. 1 came from CO2 outside. That is your first food. That is the first organic compound that the plant has made from inorganic CO2. It is not edible. But inside the stroma is phosphoglyceric acid, all kind of other compounds that will combine and break and combine and break. Enzymes will construct and deconstruct and eventually end up with a 6-carbon sugar called glucose. Okay? It's made 1 carbon at a time that came in by route of ribulose bisphosphate. So basically, the plant takes in 1 CO2, uses that carbon to assemble part of the glucose, another CO2 comes in, and eventually it has the 6-carbon sugar. Every enzymatic reaction usually requires energy. The most common energy source is the most common energy source for every cell, plant or animal on this planet is ATP made in the light reaction. So as the light reaction makes ATP and NADPH, it diffuses out into the stroma. If an enzymatic reaction needs energy, it uses those 2 metabolic energy sources to construct the glucose. Now the energy that was in the ATP is now in the glucose. Okay? Why didn't the plant stop at ATP? If it is the ultimate metabolic energy source, why didn't the plant just store ATP and use it for its enzymes whenever it was needed? If the plant can make flipping ATP and it's the ultimate energy source, why didn't it stop there? And why don't you eat ATP? I mean, it would be the ultimate doping for athletes. Shoot straight ATP in your veins, boom! I would be beating Usain Bolt. But why plants don't use ATP, don't store ATP? It is so powerful. It will destroy itself and blow apart within a matter of sometimes seconds. It cannot be stored. It's like TNT. It cannot be stored. So what the plant is going to do is use the ATP immediately as it's produced to power the enzymes to make glucose. Now, is glucose stable? Glucose is a sugar. Is it stable? Could you go home and take a sugar and put it on the counter, and would it still be there tomorrow? Could you put it in a jar and seal the lid and it would still be there next week, next month, next century? And anytime any living organism ate it, could they use it as an energy source? Yeah, glucose is the ultimate living cell energy source because it's stable. It dissolves in water so it can move to the translocation screen. It can be stored, it can be moved, it can be used. It's the ultimate chemical energy food for plants. Okay? So all this other steps leading up to glucose is the plant figuring out a way to take radiant energy, make stable chemical energy. 2 reactions, light reaction, dark reaction. Each have their own inputs and outputs. And the final product that's the miracle of the whole process is glucose. And then we're really lucky, a byproduct is oxygen. Thank you, we can breathe it. What do we exhale? CO2. Guess what? Plants thank us for that. Because some of the CO2 they use, we actually produce for them. Okay? So we're in like this mutual symbiotic relationship on this planet where we cannot survive without plants. We would have no fixed carbon, we'd have no food. But they also can't survive without CO2 being produced for them to take up. Okay? What do you need to know from all of this rigmarole? What do you need to know? Go to page 29. 29. I'm sharing. Okay, how come I can't get my annotation screen? Huh? Annotate. I want to erase. I want to erase, my friend. Doot, 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 doot. And now I want to draw again. I want you to know the net equation for photosynthesis. Everything on the left side of the equation is called an input. Everything on the right side of the equation is called an output. I want you to know where every input is used and where every output is produced. I want you to know the name of the reaction that uses it or produces it, and I want you to know where that reaction occurs inside the plant. And that table summarizes everything for you. The net equation for photosynthesis is CO2 plus water produces a carbohydrate, glucose, sugar, and a byproduct of oxygen. The water to oxygen is the light reaction that occurs in the grana of the chloroplast. That's the input and the output. The input to the dark reaction is CO2 to produce the carbohydrate, the glucose, or the sugar, whatever you want to call it. That occurs in the stroma of the chloroplast. When does the light reaction occur? In the light. It can only occur in the light. If you don't have light, you can't have chlorophyll supercharged. So it only occurs in the light. When does the dark reaction occur? Only when the light reaction occurs. Because the light reaction is feeding the dark reaction ATP and NADPH. And as soon as it stops, seconds later, the dark reaction stops. So when does the dark reaction occur? All day long. Does the dark reaction occur at night? Does the dark reaction occur at night? True or does it? How many people think dark reaction occurs at night? Raise your hand. How many people think it does not occur at night? Raise your hand. Yeah, it does not occur at night. Why in the heck did they call it the dark reaction? To mess with your mind. Oh, man. If it doesn't occur in the dark, why would they call it the dark reaction? Because in the beginning, they really thought it occurred at night until they unraveled the mechanism. And the books were all written. You know, it should have been called the non-light requiring reaction, because it doesn't require light, that only occurs in the light. Why would you do that? Okay, but if I ask you a question, true or false, the dark reaction occurs at night, the answer is false. Okay? What intermediates do you need to know other than this from what we went over and what's on that one page? The intermediates you need to know is water is split to produce an electron. You need to know that. You need to know that chlorophyll absorbs that electron. I could ask you, when water is split to produce an electron, where does the electron go? Chlorophyll absorbs it. You need to know chlorophyll is a key factor in there that absorbs radiant energy to bring that electron to a very high energy state, so that the electron transport chain can make ATP. So the two reactions of the light reaction are the splitting of water. You don't need to know it, but it's called photolysis. And the production of ATP by the electron transport chain. So you do need to know those intermediates. Split into water, produces electron, chlorophyll absorbs electron, absorbs radiant energy to supercharge the electron. That is used by the electron transport chain to make ATP and NADPH. For the dark reaction, you just need to know pretty simple. Plant takes in CO2, uses the energy from the light reaction to assemble glucose. If we could have taken a field trip, got down to the size of a molecule to go inside a chloroplast and watch it occur, I guarantee you it would have looked surprisingly exactly like what we acted out. Chemistry is not complicated if you could see it. Now, what in chemistry causes all these reactions to occur, the activation energies and all that kind of stuff, that's complicated. You don't need to know how a carburetor works to assemble a car and know it needs a carburetor. You know? You don't need to know exactly how an electron transport chain actually produces ATP, just that it does. The problem with chemistry is it's taught to you by chemistry teachers that get you down into the mud. I want you to kiss it. I want you to kiss photosynthesis. What does that mean? Keep it simple, stupid. Okay? Next time we'll show you how to manipulate photosynthesis. Thank you. And just to be safe, hey, come see. Just to be safe, I want you to disinfect your hands. Oh, crap. Did I break it? Did I just curse? Oh, but it fell off. So I didn't really curse. You can't hear me, it's not cursing. If a tree falls in the wood and doesn't make noise, it didn't make noise. Okay. I don't know if you're this cautious in your normal life, but
Oh my God.
thank you. Cool. Okay, we're gonna stop recording. Boom. Stop share. Stop recording.